the last lecture, what we saw was that if you took a linear plant which is positive real, and the definition of positive real has these ambiguities, but what we effectively would mean is that the Nyquist plot lies in the right half plane and the system, the given system is linear. Now, if you take such a plant and then such a plant is of course passive. Now, if you now take nonlinearity such that the characteristic of the nonlinearity lies in the 0 to infinity sector, then one can think of that nonlinearity also as being a passive system. As a result, what happens is when you interconnect the linear system given by a transfer function which is positive real with a nonlinearity which is in the 0 infinity sector, then you end up with a resulting system which, when you do not give any input, is asymptotically, of course, the origin is an equilibrium point of this system without inputs, and this system is asymptotically stable. In fact, when the transfer function is taken to be strictly positive real, then you can say more. In fact, you could say that the resulting system is exponentially stable. Okay. So, let me just reiterate what I have just said in terms of some diagrams, so that it would be clear to you what I am trying to say. So, what we are doing is the following. So, you have a linear plant GS, and you have this feedback connection, and you have this nonlinearity. So, this negative feedback. Okay. Now, this linear plant that you have, we are saying that this linear plant is positive real. Of course, in the last class I had given various interpretations of what we mean by positive real, but what I would mean by positive real here is that the Nyquist plot of this plant is in the right half plane, and in addition GS is stable. Okay. Of course, one could also use the definition of positive real to say that GS plus G transpose S star is greater than or equal to 0 for all real, for all S whose real part is positive. That is another equivalent definition. Okay. Now, by making this assumption, okay, so let me write down GS is positive real and stable. Okay. Now, if I call the input of this GS as U and the output of GS as Y, then what it means when you say that GS is positive, real and stable is that U transpose Y is greater than equal to V dot, where V is the storage function of GS. We have already talked about what the storage function could be, and in order to find out what the storage function could be, we invoke the positive real lemma or the Kalman-Yakubovich lemma, from where we get this matrix P. And if you recall, when you have GS to be positive, real and stable, then that is equivalent to this set of equations. That means, if you take the minimal representation for G of S to be AX plus BU, Y equal to CX plus DU, then using these matrices you can write down that there exists a P which is positive definite, and two other matrices L and W, such that first of all A transpose P plus P A is equal to minus L transpose L, and then you have P B is equal to C transpose minus L transpose W, and lastly you have W transpose W is equal to D plus D transpose. And so, this P that you get, which is positive definite, you take the storage function V to be X transpose P X, where this P is this P that you get from the positive real lemma. Okay. Now, what about the nonlinearity? Now, the nonlinearity that one picks is of the following kind. So, the nonlinearity, so let me draw that diagram once more. So, here you have the nonlinearity, we are calling this output of the linear thing U, the output Y and the input U. Okay, let me call the input of the nonlinearity psi, and let me call the output of the nonlinearity phi. Okay. Now, the nonlinearity is such that if you draw the characteristics of the nonlinearity, so you have xi on this axis and you have phi on this axis, then the nonlinearity is something that lies in the first and the third quadrant. Now, if it lies in the first and the third quadrant, then it is very clear that if you multiply the input of the nonlinearity, which is psi, to the output of the nonlinearity, which is phi, then psi or psi transpose phi, if one is considering the vectorial, the vector situation, that means multi input multi output situation, this is clearly greater than equal to 0. Okay. Now, since this is greater than equal to 0, one can say that this nonlinearity has a storage function V 1, which is the 0 storage function. Okay. Now, earlier in the last slide, I had said that you have U transpose Y is greater than equal to V dot, where this V was given as X transpose P X, with this P coming from the positive real lemma. Now, if you look here, there are these interconnection equations, which is Y is equal to psi and phi is equal to minus phi is equal to minus u. Therefore, this psi transpose phi, in fact, psi transpose phi is really equal to minus u transpose y, and this is greater than equal to 0. So, if you add this equation and this equation, you end up with 0 is greater than equal to v dot. Now, what this means is that if you use this v, that is x transpose p x, as a Lyapunov function for this closed loop system, assuming that this input, the external input is 0. So, if you have the external input to be 0, this is like a system with no inputs, and this system with no inputs will have these conditions satisfied, and if you have these conditions satisfied, then you have 0 is greater than equal to v dot, and if you take v to be x transpose p x, and that is, then that can act like a Lyapunov function for this closed loop system. And then what we have here is that its derivative is less than equal to 0. So, in fact, from that you can conclude that this resulting system is stable. Now, if you remember, we had also talked about the Kalman-Yakubovich-Popov lemma. What we had said was that if you take this thing to be strictly positive real, okay, so maybe I will mark that with black, then the change in the equations are that instead of this you will get minus epsilon p also into this equation, into this first equation. All the other equations remain as they are. But what this means is, when you substitute in here, instead of v dot being less than equal to 0, you will get 0 is strictly greater than v dot, and as a result, because of that epsilon p which is there, using the Kalman-Yakubovich lemma, if this GS was taken to be strictly positive real, then we can conclude exponential stability. Okay. So, what we are going to do in this class is we will now explore what new conclusions we can draw using this rather powerful result. Okay. Maybe before we do that, I would like to use this this V as which we have got from this positive definite matrix P as a Lyapunov function, and show that this resulting system is asymptotically stable. Well, in order to show that, I essentially only have to show that U transpose Y is greater than or equal to V dot, and then the rest of it we have already seen. That means, if you take U transpose Y greater than or equal to V dot, and you already know when you take a nonlinearity like this, that psi transpose phi is greater than or equal to 0, and when you sum both of this, you get 0 is greater than or equal to V dot. So, all you have to show is that U transpose Y is greater than or equal to V dot. Okay. One small adjustment of a constant I have to do. I should not be taking V as x transpose P x, but I should be taking this as x transpose P x by 2, half. So, now if we take that, then so we are taking to be a half x transpose P x. So, then in that case V dot is half x dot transpose P x plus a half x transpose P x dot, but we know that x dot is a x plus b u from the equation of the system of the linear system. So, substituting that in here, we will get a half of x transpose a transpose p plus from here similarly. So, P A x plus I would get half U transpose B transpose P x plus half x transpose P B U. Okay. Now, this from the Kalman-Yakubovich lemma, or rather the positive real lemma, this is the same as minus L transpose L. So, I can put that in there, and if I look at these two terms, P B, we know that one of the equations that we have from the positive real lemma is P B is equal to C transpose minus L transpose W. So, for P B I can substitute C transpose minus L transpose W, and similarly for this. So, I will just expand this out and show what that comes to. So, a half x transpose P B U becomes a half x transpose C transpose U plus or rather minus a half x transpose L transpose W U. Okay. Now, if you look at the output equation of the linear plant, you have y is equal to C x plus d u, and so the C x I can substitute is y minus d u, and once I do that, I get a half y transpose u minus a half u transpose d transpose u. So, this is from this x transpose p b u. From this thing, you would get exactly the transposes of this. So, when you put them all together, then you end up with v dot is equal to minus a half x transpose L transpose L x, that accounts for this, and then from both of this you will end up with u transpose y, because this half and then be another half coming from there, and then you have this term and there will be a similar term coming from the other portion, and so putting both of them together you will have u transpose d transpose u, and you will have u transpose d u, and d plus d transpose one of those equations that you had was D plus D transpose is equal to W transpose W. The positive real lemma gave us this equation. So, using that you will get U transpose W transpose W U, a half of that. Okay. And then these last two terms, which okay, so there will be this term and the transpose of this, both with a minus sign. And so, if I put all of them together, then what I end up with is V dot is equal to, first of all, U transpose Y, which we had here, and then these two terms and the other two terms, this and its transpose, putting them all together, you will get minus half L x plus W u, the whole thing transpose L x plus W u. And now you see this quantity here is positive quantity, and therefore, you can conclude V dot is less than or equal to U transpose Y, and this is essentially what we wanted in order to conclude from this sheet that U transpose Y is greater than or equal to V dot, 0 is greater than, and you already have this about the nonlinearity, and when you put both of them together, you get 0 is greater than or equal to V dot, and therefore, you can show stability. Now, if one assumes that G of S is strictly positive real, then in that case, in this equation here, A transpose P plus P A, there will be one additional term here, and this additional term, if I call it epsilon P, this additional term will finally end up in the last equation, and here you would have minus epsilon x transpose P x, and this will now let us prove that the resulting system is in fact asymptotically stable. Now, what I am going to do is I am going to make use of this rather powerful theorem, and I am going to look at all kinds of nonlinearities and derive new results about which nonlinearities with when put in a feedback connection with a certain kind of linear plant would result in an asymptotically stable system. Okay. So, let me conclude about this first. So, what I am saying now is, suppose you take a nonlinearity well, let me call it F, that belongs to the 0 infinity sector. Now, when I say that a nonlinearity belongs to a 0 infinity sector, what I mean by that is that if psi is the input of the nonlinearity and this is f of psi, the output of the nonlinearity, then this nonlinearity lies in the 0 to infinity sector. That means, it lies either in the first quadrant or in the third quadrant. Okay. If you have any such nonlinearity, any nonlinearity which belongs to this class, and you take a G of S which is stable and strictly positive real, then this feedback connection of the strictly positive real stable plant with the nonlinearity results in something which is asymptotically stable. But suppose now the nonlinearity that we consider is this particular nonlinearity. Now, if you consider this particular nonlinearity, then you can see that of course, it is true that this nonlinearity lies in the 0 infinity sector, but in fact, you can say more things about this nonlinearity, because suppose I draw a slope like this, call it k 1, and suppose I draw another slope, let us say like that, call it k 2, then in fact, this nonlinearity f lies in the K1, K2 sector. So, what I am trying to say is that the nonlinearity is such that K1 is less than equal to f xi by xi, which is less than equal to K2. So, in some sense, by declaring f to be in this sector from 0 to infinity, we are doing an overkill, because we can get a much tighter bound for the nonlinearity, and in fact, we can say that the nonlinearity lies in the sector K1, K2. In fact, out here, as you can see, okay, so here the way I have drawn it, of course, the K2, there is some portion here of the characteristic which has the slope K2, but instead of writing this, sometimes people would write something like this, K1, K2, an open interval K1, K2. Now, when you mean an open interval K1, K2 or a closed interval K1, K2, the difference between them is essentially to do with these inequalities, whether they are strict inequalities or just non-strict inequalities. So, when you have non-strict inequalities, then you would put the closed bracket. When you have strict inequality, you would put the open bracket. Yeah, and of course, there would be semi-open, semi-closed kind of intervals also for the nonlinearity. Okay. Now, fine, because this nonlinearity lies in the 0 infinity sector, therefore, we know that if you take any stable strictly positive real transfer function and connect it in this feedback loop with this particular nonlinearity, you will get an asymptotically stable system. But since we can put a tighter bound on this nonlinearity, that means this nonlinearity actually lies in the K1, K2 sector, therefore, one would expect that apart from these plans, there are other plans also which you could connect with this nonlinearity, and these plans may not be belonging to this class. That means, they may not be strictly positive real or stable, but despite that the resulting system is asymptotically stable. And the reason why one would believe that is because it is true that this particular nonlinearity is in the 0 infinity sector, but in fact, we can say that it is in the K1, K2 sector. And so, if it is in the K1, K2 sector, it would be very surprising if there are no extra plans that one can connect to the nonlinearity, resulting in the system being stable. I mean, one would naturally expect that there would be more plans that you can connect to the nonlinearity, and the resulting system is asymptotically stable. Okay. So, now what we are going to do is we are going to explore this situation where you have the nonlinearity given in a certain sector, and one wants to characterize all the transfer functions which you can connect in this feedback loop with those nonlinearities, such that the resulting system is asymptotically stable.